Greetings, students. This is Mr. Allen, your calculus teacher, and today's lesson is on section 2.8, something called Newton's method. Now, you may be wondering, wait a minute, Mr. Allen, I thought we were starting with chapter 3. We are, but I'm going back and we're going to look at chapter 2 for this section because this is actually a section I don't believe that was covered last year, and it is part of the BC curriculum, so I'm covering it now. Newton's method, hopefully you know that Newton is referring to someone by the name of Isaac Newton. So the objective for this lesson is to approximate a zero or zeros of a function using Newton's method. In this section, we'll study a technique for approximating the real zeros of a function. This technique is called Newton's method, and it uses tangent line approximation of the graph of a function near its x-intercept. Now remember, a zero is where it crosses the x-axis, so that's why we're making this connection here. To see how Newton's method works, consider an arbitrary function f that's continuous on some interval ab and it's differentiable on the open interval ab. If f of a and f of b differ in sign, then by the intermediate value theorem, we know that it has to have at least one zero. In other words, if we know that f of a is, let's say, 2, and f of b is, let's say, -1, we know that there's a change in sign, so there has to be every value between those two, so there has to be a 0. So to estimate the 0, we're just going to pick an x value, and we'll call it x1. That's our first estimate, so we just guess that's our 0 now. Now the actual 0 is here at c, but we're just going to pick some value of x that's close. Newton's method is based on the assumption that the graph of f and the tangent line both cross the x-axis at about the same point. So you can see here that when I pick x1 and I draw my tangent line, the curve hits actually right there on the x-axis, which isn't c, but it's pretty close. Because you can easily calculate the x-intercept for this tangent line, you can use a second estimate, which is going to hopefully give us a better answer, and it typically does. The tangent line that passes through the point x1, f of x1, with the slope of x prime x1, is this formula right here, which you should be familiar with. It looks very similar to our y minus y1 equals m times x minus x1. That's how we write the equation of a tangent line. So then we can go ahead and move this term over to the right-hand side, and it would look like this. Now, if we're looking for the x-intercept, then that means y is equal to 0. So if I change this y to 0, I can solve the equation, and it will give me this. This is essentially the formula that we're going to be using. X equals x1 minus f of x over f prime of x1. So from our initial estimate of x1, we obtain a new estimate. So now we have x1, we want it to be better. So now we're going to find x sub 2, so that's going to be our next guess. So now we draw our tangent line over here, it gives us this. Now notice that x3 is closer to c, much closer than x1 was. Still not c, but it's better. And then we can get even better still, so we'll do another estimate. We'll do x3, that's our third estimate. This is an iterative process that you can repeat, and you can basically get your 0 as close to the actual value as you'd like. So this is probably the most important slide in the notes. It gives us the technique for finding zeros using Newton's method. You make your initial estimate, x sub 1. It would be nice if you pick that value to be close to the actual 0. So for example, if you think the 0 is at 0.5, then you want to make your initial guess close to 0.5. Here's our formula. Again, this is the meat and potatoes of it. And then this third option here is just when you're actually looking for a certain degree of accuracy. I'm not going to focus too much on that. I just want you guys to get a feel of Newton's method. Again, this is an iterative process. The more steps you do, the more accurate it's going to be. It's actually pretty efficient. So let's look at an example here. So we have our function f of x equals x squared minus 2 we know that this probably crosses the x-axis somewhere. You probably already can guess where it crosses, but we're going to pretend that we don't know. We're going to make our initial guess at 0. I'm sorry, at x sub 0 equals 1. So we're going to make our initial guess at 1. Now, clearly, 1 is not the 0 here. If you plug 1 in there, you don't get 0. Before I start working this example, I want to forewarn you that I have worked out these numbers beforehand to speed this process up to keep the video fairly short. So you would have to do this, you know, it's going to take you a little bit longer at first. So our key formula here is as follows. X sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. This is our formula. You can see this on the previous slide right there, okay? So in this particular example, we already know what x sub 0 is. We already know what f of x is. What we don't know in this formula is we do not know what f prime is. And f prime is very simple. That's using our rules for derivatives. It's just power rules. So that's 2x. So now we have all that we need to know. So let's go ahead and use a different color here. If I want to find x sub 1, which is going to be after my initial guess was x sub 0. So x sub 1 is going to be my first guess, or my first calculation. So I got to put an x sub 1. Now, if this is x sub 1 over here, what would this have to be? Well, this is x sub n plus 1, so this must be x sub 0. So this is x sub 0 minus f of x sub 0 divided by f prime of x sub 0. In other words, it's going to be 1 minus f of 1 over f prime of 1. So now let's go ahead and figure out what that's going to be. So I'm going to do that in green. So that's going to be 1 minus whatever f of 1 is. So I got to plug 1 into my original function. That gives me -1. And I also have to plug 1 into my derivative function, which is 2x. So that's just going to give me a 2. So that tells us that x sub 1 is 3/2. So our first guess, our initial guess, was 1. Our new guess now, x sub 1, is 3/2. This is an iterative process, so I want an even better guess, or a better calculation. So we're going to continue the process. Now, I already know what x sub naught is. That was our first guess. We've just found that x sub 1 is 3/2. Now let's go ahead and see if we can figure out what x sub 2 is going to be. Well, x sub 2 is going to be x sub 1 minus f of x sub 1 divided by f prime of x sub 1. In other words, what we're going to get here is, and I'll just go ahead and use green, we're going to get 3/2, that was x sub 1, minus f of 3/2, that's 3, sorry, it's ugly 3, divided by f prime of 3/2. Again, that's 3/2. And I've already done all of this work, but I'm going to go ahead and show you the steps anyways. Minus, and then that numerator there is going to be 1/4, and then the denominator here turns out to be 3. Now, I've already done this work. So that tells me then that x sub 2 turns out to be 17/12. Now, just to give you some idea of what that is as a decimal, that's approximately 1.4167. Let's go ahead and do it one more time because the problem asks us to find, I think it tells us to do 3 iterations. We've only done 2 now. So to find x sub 3, I would recommend, actually what might be good for you to do right now is pause the video and actually see if you can calculate x sub 3. To find x sub 3, I'm going to do x sub 2 minus f of x sub 2 over f prime of x sub 2. And by the way, this is x sub 2. Actually, I probably would use the fraction of it. And I'm just going to tell you that when you calculate this one, it turns out to be 577 over 408, which is approximately 1.4142. Now, question. Does anybody know what that number is kind of close to? It should look like a very common number. I guess not super common, but do you know what that number is? I'll give you a hint. What do you think the solution is for this equation if it's set equal to 0? Hopefully you're thinking what I'm thinking, but let's go ahead and go to the next slide. So this next slide here, I've actually got a table of all the work kind of worked out. Over here are our answers. So that 1.5, that's the same thing as 3 over 2. This was our second answer there, was 17 over 12. And then here's our third answer, which was that 577 over 408. I want to figure out what that number is. Well, I'm going to let the cat out of the bag. You probably already guessed it. It's the square root of 2. Now, you'll notice here it says that in this case, we know we have 2 zeros. The function is plus or minus square root of 2. Hopefully, you realize that in our function here, let's see how much more I got here. Yeah, so our original function was f of x equals, I think it was x squared minus 2. Guys, that's going to be a parabola, right? That's going to be a parabola that is opening up like this, and it's going to cross the x-axis here and here, and that's going to be the square root of 2 over here, and that's going to be negative square root of 2 over there, which you already knew that. You could have done that with algebra. But anyways, so after 3 iterations, we have 6 decimal places, and after those 3 iterations, we are within, that's going to be 10 hundredths, thousandths, 10 thousandths, 100,000, 2 1,000,000ths of the exact answer. 2 1,000,000ths. That's pretty accurate for only 3 iterations. It's pretty accurate. Oh, and there's the picture here. I guess I should have, let me go ahead and clear off all of this so you can see the picture. So here's the picture. So our initial guess was 1. After our first computation, now notice here it says x sub 1. I kind of stole this out of the book. That was our x sub 0. This is actually our x sub 1 right here. And we know that the actual answer is going to be the square root of 2. Within example 1, the approximation approaches a limit. In other words, we're getting, as we continue that Newton's method process, we are going to get closer and closer to the square root of 2. It actually would take us an infinite number of steps to actually get to the square root of 2, but you guys already know that square root of 2 is infinite, an irrational number. So we say that it converges. This is a word that we're going to use a lot this, particularly second semester. We say that these values converge. Moreover, when the limit is c, it can be shown that c must be a 0 of f. Newton's method does not always yield a convergent sequence. So I wanted to warn you about this. So this is a warning. If you start doing, a warning, when you start doing Newton's method, if your successive values get further and further apart, you've got a problem. So let's say your first guess was x naught equals 1, and then x1 is, let's say, 3/2. But then x2 turns out to be 2, and then x3 turns out to be 4 or something, and the values are getting further and further apart from something. That's a pretty good indication that you've got a problem, Houston. Newton's method does not always work. It works a lot, but not always. Because Newton's method involves division by f prime of x sub n, it's clear that when that derivative is not defined or 0, we've got a problem. When you encounter this problem, you can usually overcome it by just pick a different value of x sub 1. It can be shown that a condition sufficient to produce convergence of the Newton's method can be produced using the following condition. In other words, if you've got a function, if you can show that the absolute value of f of x times the second derivative of f of x divided by the first derivative of f of x squared is less than 1, then we know that it's going to converge on that open interval, and we'll be able to find a 0. So for example, in the problem we just did, f of x was x squared minus 2, f prime was x squared, f double prime, of course, would be 2. So then if we plug this information into our formula up here, you will see that this turns out to be the following, and that is going to be less than 1. Now, I'd like you to think about why that's going to be less than 1. but it's going to be less than 1. And I think I'm going to go ahead and end the presentation here.